Hello student, welcome back. Lecture 6, Module 1, Microcontroller and Embedded System. Songita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. In the previous lecture, we have explained the pin diagram and the programming model of 8051. Now today's content, the port structure and operation, timer, counters, serial interfaces and external memory. Input-output ports, I/O ports of 8051. All 8051 microcontrollers have 4 I/O ports, each comprising 8 bits, which can be configured as inputs or outputs. Accordingly, in total of 32 input-output pins enabling the microcontroller to be connected to peripheral devices are available for use. Pin configuration, that is to whether it is to be configured as an input 1 or an output 0 depends on its logic state. In order to configure a microcontroller pin as an input, it is necessary to apply a logic 0 to appropriate I/O port bit. In this case, voltage level on appropriate pin will be 0. Similarly, in order to configure a microcontroller pin as an input, it is necessary to apply a logic of 1 to appropriate port. In this case, voltage level on appropriate pin will be 5 volt. As in the case with any TTL input. This may seem confusing but doesn't lose your patience. It all becomes clear after studying a simple electronic circuit to an I/O pin. Input-output I/O pin. This is shown in the figure. Figure above illustrates a simplified schematic of all circuits within the microcontroller connected one of its pins. It refers to all the pins except those of P0 port which do not have pull-up resistor built in. Output pin. A logic 0 is applied to a bit of the P register. The content Fe transistor is turned on, thus connecting the appropriate pin to ground. Input pin. A logic of 1 is applied to a bit of the P register. The register is shown over there. The output Fe transistor is turned off and the appropriate pin remains connected to the power supply voltage over a pull-up resistor of high resistance. Logic state of any pin can be changed or read at any moment. A logic 0 and logic 1 are not equal. A logic 0 represents a short circuit to ground. Such a pin acts as an output. A logic 1 is loosely connected to the power supply voltage over a resistor of high resistance. Since this voltage can be easily reduced by an external signal, such a pin acts as an input. Now this port 0. The P0 port is characterized by two functions. If external memory is used, then the lower address byte, the address byte is A0 to A7, is applied on it. Otherwise, all bits of this port are configured as an input-output. The other function is expressed when it is configured as an output. Unlike other ports consisting of pins with built-in pull-up resistor connected by its end to 5 volt power supply, pins of this port have this resistor left out. This apparently small difference has its consequences. If any pin of this port is configured as an input, then it acts as if it floats. Such an input has unlimited input resistance and indeterminate potential. When the pin is configured as an output, it acts as an open drain. By connecting and applying logic 0 to a port bit. The appropriate pin will be connected to 0 volt or ground. By applying logic 1, the external output will keep on floating. In order to apply logic 1 5 volt on this output pin, it is necessary to build in an external pull-up resistor. Part 1. Part 1 is true. This is port 1. This port 1 is true IO port because it does not have any alternative function as in the case of P0, but it can be configured as general IO only. It has a pull-up resistor built in and is completely compatible with TTL circuits. P2 port. P2 acts similarly as P0 when external memory is used. Pins of this port occupy addresses indented for external memory chip. This time it is about the higher address byte with addresses A8, A15. When no memory is added, this port can be used as a general input-output port showing features similar to P1. P3, port 3. All port pins can be used as general IO, but they also have an alternative function. In order to use this alternative function, a logic 1 must be applied to appropriate bit of the P3 register. In terms of hardware, this port is similar to P0, with the difference that its pin have a pull-up resistor built in. Now the pin diagram of 8051 and ports. 8051 members come in different IC packages such as DIP dual inline package, QFP quad flat package and LLC leadless chip carrier. They all have 40 pins that are dedicated to various functions such as IO, RD, WR, address, data and interrupts. Some companies provide 20-pin version of the 8051 with a reduced number of IO ports for less demanding applications. Majority of developers uses the 40-pin chip. We will concentrate on that and the figure shows the pin diagram of 8051. 8051 microcontroller with 40 pins. A set of 32 pins are set aside for the 4 ports P0, P1, P2 and P3, where each port takes 8 pins. Pin 40 provides supply voltage to the chip. The voltage source is plus 5 volt. Pin 20 is the ground. The rest of the pins are designed as XTAL1, XTAL2, RST, EA, PSEN and ALE. XTAL2 and XTAL1 are 4 oscillator input which provides the check and clock pulse to microcontroller. The pins from 32 to 39 from the port 0, AD0 to AD7, port 0.0 to port 0.7 are multiplex pins used for address and data. The pins from 1 to 8 are for port 1 for 0 to port 1 for 7 and pins from 21 to 28 are for port 2 from port 2 0 to port 2 7 is used for sending or transmitting. The ninth pin RST is used for restarting the 8051 microcontroller. The pins from 10 to 70s are for port 3, which is a special port and it is multifunctional. The 38th pin is ALE, address latch enable. When the pin is set to 1, then address is transferred through the pins AD0 to AD7. When the pin is set to 0, then the data is transferred through the pins AD0 to AD7. The 29th pin is PSEN, which is the program strobe enable used for reading the program from the external memory. Now the crystal oscillator. Crystal oscillator connection to the external clock source. The 8051 has an on-chip oscillator but requires an external clock to run it. Most often a quartz crystal oscillator is connected to the XTAL pin 19 and XTAL pin 18. The quartz crystal oscillator connected to inputs XTTL1 and XTTL2 also needs two capacitors of 30 picofarad value. One side of each capacitor is connected to the ground as shown in the figure. It must be noted that there are various speeds of 8051 family. Speed refers to the maximum oscillator frequency which is connected to XTL. For example, a 12 MHz chip must be connected to a crystal with 12 MHz frequency or less. Likewise, a 20 MHz microcontroller requires a crystal frequency of no more than 20 MHz. When 8051 is connected to a crystal oscillator and is powered up, the frequency on the XTAL2 pin is connected using oscilloscope. The 8051 has an on-chip oscillator but requires an external clock to run it. Most often, a quartz crystal oscillator is connected to input XTAL pin 19 and XTAL pin 18. The quartz crystal oscillator connected to its XTAL1 and XTAL2 also needs to RST and EA. Now RST 9, pin 9 is the reset pin. It is an input and is active high. When the pin is applied to high, the microcontroller will reset and terminate. EA. The 8051 family members will come with an on-chip ROM for storing the programs. In such cases, the EA pin is connected to VCC. For the family members like 8031 and 8032, there is no on-chip ROM. Hence, the code is stored in external ROM and is fetched by 8031 and 8032. EA pin is connected to ground to indicate that the code is stored in external memory or externally. EA stands for external access, which is pin 31 in the DIP packages. It is an input pin and is connected to either VCC or ground. 8031 uses the pin along with PSEN to access programs stored in ROM memory located outside 8031. The next two pins are used mainly in 8031 based systems. PSEN, program stored enable. This is an output pin. The external ROM holds the program code. This pin is connected to the OE pin of ROM. ALE. It is an output pin and is active high when connecting an 8031 to external memory. Port 0 provides both address and data. The ALE pin is used for demultiplexing the address and data by connecting to G pin of the 874 LS373 chip. Port 0, port 1, port 2 and 3. All the 4 ports in 8051 are bidirectional. Each consists of a latch and output driver, an input buffer. P0, P2 and P3 will perform special function other than I/O. As shown in figure below, there are 4 ports, namely P0, P1, P2 and P3. Each uses 8 pins, making them 8-bit ports. All the ports upon reset are configured as input since P0 to P3 have FFH on them. So this is the port 0 with pull-up registers. Here shown the 8 output pins for P0, P00, P01, P02, P03, 4, 5, 6 and 7, and it is connected, and as a whole this is P0, and there are 10K pull-up resistor connected to supply voltage. The output drivers of port 0 and 2 and the input buffers of port 0 are used in access to external memory. In this application, port 0 outputs the lower byte of the external memory address. Time multiplex with the byte being written or read. Port 2 outputs the high byte of the external memory address when the address is 16-bit wide. As shown in the figure, port 0 is also designed as AD0 to AD7, allowing it to be used for both address as well as data. When connecting 8051 to an external memory, port 0 provides both address and data. The 8051 multiplexes address and data through port 0 to save pins. ALE indicates if port 0 has address or data. When ALE is 0, it provides data D0 to D7. But when ALE is equal to 1, it has address A0 to A7. Therefore, ALE is used for demultiplexing the address and data. When there is no external memory connection, the pins of P0 must be connected externally to a 10k ohm pull-up resistor. This is due to the fact that P0 is often open drain, unlike P1, P2 and P3. Open drain is termed used for MOS chip in the same way that is as that of TTL open collector chip. In contrast to port 0, P1, P2, P3 do not need any pull-up resistor since they have pull-up resistor internally. Upon reset, ports P1, P2, P3 are configured as an input ports. P1 and P2. In 8051 based systems with no external memory connection, both P1 and P2 are used as simple I/O. However, in 8031, 8051 based systems with external memory connection, port 2 must be used along with port 0 to provide the 16-bit address for external memory. Port 2 is designed as A8 to A15, indicating its dual function. When 8051 is connected to external memory, P2 is used for the upper 8 bits of the 16-bit address and it cannot be used for I/O. Port 3, it occupies a total of 8 pins, pins 10 to pin 7. It can be used as input or output ports. Port P1 and P2 and P3 does not need any pull-up resistor. Port 3 has the additional function of providing some extremely important signals such as interrupts. Port 3.0, 3.1 are used for receiving data and transmitting data serial communication signals. Hence, 8051 supports parallel as well as serial communications. Bits P3.2 and 3.3 are set aside for external interrupts. Bit 3.4 and 3.5 are used for timer 0 and timer 1. P3.6 and 3.7 are used to provide the read and write signal for external memory connection, while the reset of pins in port 3 are normally used for alternate function role. Now the port 3 alternate function. Now port 3.0, it is for receiving serial input and pin number is 10. Port 3.1 for transmitting serial output port, it is pin number 11. Port 3.2, it is INTO external interrupt, pin number 12. Then pin number port number 3.4 TO timer or counter 0 external input, pin number 14. Then come pin number 15, it is timer 1, timer or counter 1 external input, it is port 3.5. Port 3.6 for writing external data memory, write strobe, it is pin number 16, and pin number 17 is for reading external data memory, read strobe, it is pin number 3.7. Initially, bit P01 is set as an input port, then the hexadecimal value FFH is stored in accumulator. The jump condition fails and the accumulator value is sent to the port 2, P2. Then the port P1.2 is cleared and it is set again for giving the low to high pulse to the port P1.2. Then the alarm will ring. If the switch is pressed, the LEDs connected to P2 will glow and the alarm will be start ringing. 8051 timers and counters. The 8051 has two counters, timers, which can be used either as timer or to generate a time delay or as counter to count events happening outside the microcontroller. 8051 has two timers, timer 0 and timer 1, then can be used as timer as well as counters. Both timers are 16 bits wide. Since the 8051 has an 8-bit architecture, each 16-bit is accessed as two separate registers of low byte and high byte. First, we will discuss about timer 0 register. So this is timer 0. It is of total 16 bit. The lower 8 bit is as T low and higher bit is T high, TH, and it is TL0, it is TH0. Timer 0 register is a 16-bit register accessed as low byte and high byte. The low byte is referred to as TL0 and the high byte is referred as TH0. This register can be accessed like any other register. Timer 1 register is also 16-bit. It is TL1 and TH1, total of 16-bit. It is timer 1. Now TMOD, timer mode register. This is a 8-bit register which is used by both timer 0 and timer 1 to set the various timer modes. In this T-mode register, the lower 4 bits are set aside for timer 0 and the upper 4 bits are set aside for timer 1. In each cases, the lower 2 bits are used to set the timer mode and the upper 2 bits are specified for the specific operation. Upper and lower 4 bits. In upper and lower 4 bits, the first bit is a gate bit. Every timer has a means of starting and stopping. Some timers do this by software and some by hardware, and some have both software and hardware controls. The hardware way of starting and stopping the timer by an external source is achieved by making gate equal to 1 in the T-mode register, and if we change to gate equal to 0, then we do not need external hardware to start and stop the timers. The second bit in time C or T bit is used to decide whether the timer is used as a delay generator or an event counter. If it is 0, it is used as timer. If it is 1, it is used as counter. The upper and the lower 4 bit, the last bit, third and fourth, are known as M1 and M0 respectively. They are used to select the timer mode. So when M0, M1 and mode, this is a combination. When this is 000, the operating mode is 13-bit timer mode, 8-bit timer or counter, THX and TLX are 5-bit prescaler. When it is 011, 16-bit timer mode, 16-bit timer or counter, THX and TLX are cascaded and there are no prescaler. When it is 102, 8-bit auto reload mode, 8-bit auto reload timer or counter, THX holds a value which is to be reloaded into TLX each time it overflows. 113 split timer mode. Mode 0. Mode 0 is exactly same like mode 1 except that it is a 13-bit timer instead of 16-bit. The timer 13-bit counter can hold values between 0000 to 1FFFH in TL to TL, TH to TL. Therefore, when the timer reaches its maximum of 1FFH, it rolls over to 0000 and TF is raised. Mode 1. It is a 16-bit timer, therefore it allows values from 000 to FFFFH to be loaded into the timer's register TL and TH. After TH and TL are loaded with a 16-bit initial value, the timer must be started. We can do it by ACTB TR0 for timer 0 and ACTB TR1 for timer 1. After the timer is started, it starts counting up until it reaches its limit FFFFH. When it rolls over from FFFF to 0000H, it sets high a flag bit called TF timer flag. This timer flag can be monitored. When this timer flag is raised, one operation would be stop the timer with the instruction CLR TR0 or CLR TR1 for timer 0 or timer 1 respectively. Again, it must be noted that each timer flag TF0 for timer 0 and TF1 for timer 1 after the timer reaches its limit and rolls over. In order to repeat the process, the registers TH and TL must be reloaded with original value and TF must be reset to 0. Now mode 2. It is an 8-bit timer that allows only value of 00 to FFH to be loaded into the timer's register TH. After TH is loaded with 8-bit value, the 8051 gives a copy to it to TL. Then the timer must be started. It is done by instruction ACTB TR0 for the timer 0 and ACTB TR1 for timer 1. This is like mode 1. After the timer is started, it starts to count up by incrementing the TL register. It counts up until it reaches its limit to FFH. When it rolls over from FFH to 00H, it sets high to TF timer flag. If we are using timer 0, TF0 goes high. If it using TF1, then TF1 is raised. When T1 register rolls from FFH to 00 and TF is set to 1, TL is reloaded automatically with the original value kept by the TH register. To repeat the process, we must simply clear TF and let it go without any need by the programmer to reload the original value. This makes mode 2 auto reload. It contrasts in mode 1 in which programmer has to reload TH and TL. Mode 3. In mode 3 is also known as split timer mode. The timer 0 and 1 may be programmed to be in mode 0 and 1 and 2 independently of similar mode for other timer. This is not true for mode 3. Timers do not operate independently in mode 3 is chosen for timer 0. Placing timer 1 in mode 3 causing it to stop counting. The control bit TR1 and the timer 1 flag TF1 are then used by the timer 0. Tcon register bits. Now bits and symbol and function for every bits of tcons are as follows. So the LSB is IT0, then IE1, then IT1, then IE1, TR0, TF0, TR1, TF1. Now bit and its corresponding symbol and function. Bit 7 TF1 timer 1 overflow flag set when timer rolls from all 1s to 0, cleared when the processor vectors to execute interrupt service routine, locating at program address 001BH. 6 TR1 timer 1 run control bit set to 1 by programmer to enable timer to count, cleared to 0 by program to halt timer. 5 TF0 timer 0 overflow flag same as TF1. 4 TR0 timer 0 run control bit same as TR1. 3 IE1 external interrupt 1 H flag not related to timer operation. 2 IT1 external interrupt 1 signal type control bit set to 1 by program to enable external interrupt 1 to be triggered by a falling edge signal, set to 0 by program enable a low level signal on external interrupt 1 to generate an interrupt. 1 IE0 external interrupt 0 H flag not related to timer operation 0 IT0 external interrupt 0 signal type. It is register bank 1. First one is register bank 0, then register bank 1. It is started from 08H to 0F. Bits in PSW register. Next 16 by 16 bytes are bits addressable in total by 16 into 8 lower element H to 7FH MSB of the last byte in 2FH. Remaining 80 bytes of RAM are available for general purpose. So internal data memory map. The internal data memory and special function register SFR map. 0 to 7FH is direct or indirect addressing SFRs, direct addressing SFRs. The special function register